The second part of 15.2 is looking at spontaneity, which stems directly from entropy and ties it all together. So what is spontaneity? Spontaneity is looking at total entropy, not just in the system, but in the system and the surroundings and all available energy to figure out how a reaction is going to move forward, or even if a reaction is going to move forward. Total entropy change is a look at the change of a substance in a reaction and its surroundings. So let's say we have our beaker. In our beaker, we've got our reaction going on, right? We've got our thermometer tracking the temperature change. And we start to see that the thermometer is decreasing in temperature, which means heat is escaping, correct? All right, so what this means is the entropy of our surroundings has increased. Why is that? Well, that is because heat is being given off and going from the system to the surroundings. So the entropy of the surroundings is increasing. That means the disorder of your surroundings is also changing. And we can look at that in the terms of the system as well. But you have to know that both the system and the surroundings are affected during a reaction. So this actually has a calculation we can use with it. The calculation is the delta S, so change in entropy of the total. And so looking at the total entropy change, that takes into account the change of the surroundings and the change of the system. Well, the system we can directly measure with a thermometer, right? How can we look at the surroundings? And that's a lot more difficult to measure because you have to look at the surface area of the glass where you're using, or if you're using more of a foam container or closed system, you're not going to have something in the surroundings. So you need to be able to measure it. We can do this by the fact that the surroundings, the delta S of surroundings, so the entropy of the surroundings, is affected by the delta H of the system. That is because if the delta H is an exo or it's an endo reaction, if it's an exo, that means heat is giving to the surroundings. If it's an endo, heat is coming from the surroundings, and that's going to change the disorder. And surroundings are going to be affected by temperature, because temperature, as we know, changes the movement of the average kinetic energy of the particles, and therefore, going to entropy, right? So how can we work these two things, which we can measure? Because delta H of a system, we learned back in 5.2 and 5.3 and so on and so forth. We've been learning about that one. And then, of course, we can measure temperature. So how we can relate these two? Well, delta S of the surroundings is proportional to the negative delta H of the system. So when you're looking at this, think back to our MCAT reactions, where the delta H of the reaction equals the negative delta H of your water. So kind of same thing. What's happening to the surroundings is the opposite of what's happening to the system, right? Which is why we have that negative value. And then the delta S of the surroundings is proportional to 1 over temperature. And so this all depends on the surrounding starting temperature. So if the surrounding temperature is hot, so we're working in a hot classroom, it's a hot day, whatever, those molecules already have a lot of average kinetic energy. So any entropy being added, you're going to see a small change. And we can do this all by predicting. If it is a cool day or cold surroundings, so on and so forth, and you're adding energy to it, you're going to see a big change. And so that can help explain why you're seeing the changes you do in a reaction. We expected something much larger, so on and so forth. We expected a bigger change. Well, we have to take into account that the surroundings are also interacting, the particles in the surroundings are also interacting with that reaction. So essentially, we can go through and we can say delta S of surroundings is equal to the negative delta H of your system over temperature of the surroundings. These two things we can measure, and so since we can measure those two things, we can figure out the delta S of the system based off calculations that we learned about in the first video of 15.2. We can then figure out the total delta S of a reaction. So spontaneous change. With spontaneous change, or how we can calculate spontaneous change, and no, this is not spontaneous combustion of a human. Nice try. But that is spontaneous change of a reaction. So theoretically, a human could spontaneously combust, but we're made of so many different reactants, they would combust at different times, so you'd actually just die from something else before you spontaneously combust, just to let you know. So we take the delta S, the total change of entropy equals the total change in entropy of your surroundings plus the total entropy change of your system. And that value needs to be greater than 0. And for the most part, because it's going to be greater than 0 and looking at it, that happens for exothermic reactions. Endothermic reactions can occur if the delta S of your system can compensate for the negative delta S of the surroundings as heat flows into the system, even though they are rare. All right, so here we have our reaction. I went through and I already substituted what we did on the previous slide. So we already found out that we can take this delta S of your surroundings and substitute in measurable features. So now we have the delta S of total equals the negative delta H of your system over temperature plus the delta S of your system, which we can calculate. And that all is going to be greater, or that value is going to be greater than 0. So we're going to manipulate this this calculation a little bit. Okay, because dividing one value by t doesn't make sense, so we're going to get rid of that t, right? So, and we're going to move it, so we're going to multiply it. So now you see we have t delta S total, H is now by itself, and then t delta S is greater than greater than 0. Now when we're thinking of this, and the reason we have the negative delta H, but when we go look at free energy, we always associate free energy with as a negative value. And so what happens when we go through and finish manipulating it, we take the inverse of everything. So now we have negative T delta S equals delta H, that's your system, minus T delta S. And that value is going to be less than 0. And this numerically helps us understand free energy and spontaneity and helps us make sense of it with the values of delta H and delta S, whereas if we kept it in the previous calculation, just conceptually speaking, it makes it a little bit more difficult. All right, so this whole process of spontaneity is actually called Gibbs free energy. And so the calculation of Gibbs free energy is delta G of the system, and guess what that is if you look at this reaction? Delta G of the system is negative T delta S total. So this block and this value right here, we just say is delta G, and that is Gibbs free energy, and that is the amount of energy available to do useful work. And so that equals delta H minus T delta S. As we know already, delta H is the quantity of heat change occurring due to the reaction. We know delta S is what direction is entropy going. Is it going towards more disorder or towards order? And what delta G is the quality of heat change. So we're numerically determining how valuable or how much energy is available to do useful work. And so we say it's free, quote unquote, energy when it does useful work rather than losing that work to heat loss. When we go through and do this calculation, if delta G comes up with a negative number, it is a spontaneous reaction. If delta G is a positive number, it is a non-spontaneous reaction. So in between, when delta G equals 0, that reaction is at what we call equilibrium. And so it's essentially the tipping point between non-spontaneous and spontaneous. One of the things we can do with delta G is predict the feasibility of change. How much work are we going to need to put into this reaction to actually push it forward, or is it just going to happen? And this is going to go into industry determining how much cost are we willing to pump in, how much electricity, heat, whatever it is, and we can still make a profit. And at what temperatures do we need to run a reaction? And so it's a whole cost benefit analysis that can be run with Gibbs free energy. So delta G is affected by the change in temperature. As we see, temperature is part of the reaction which we're working with, right? So delta G of the system equals delta H of the system minus T delta S. So you will see questions on, well, if the reaction's being run at a high temperature, what is going to be the sign of delta G? You need to play the sign game, all right? So you need to go through and figure out what's going on. If delta H is negative, right, we get a negative number. And if delta S is negative, okay, so negative times a negative gives you a positive. So the bigger the delta T, the more likely you're going to have a delta G positive value, right? If you have a delta H that is positive and you have a delta S that is negative, again, a negative is a positive, delta H is positive. No matter what the temperature is, you're going to have a positive delta G. It's not going to be spontaneous, right? If you have a negative delta H and you have a positive delta S, well, a positive is always a minus, so it doesn't matter the temperature because you're only making that minus bigger, right? And so you're always going to have a delta G negative. So you don't really need to put values in there. You just need to understand at certain temperatures the sign may change and overpower, and therefore you're going to see a movement toward spontaneous or non-spontaneous reaction. So let's look at an example of how to go through the delta G calculation. So we have water, and we have liquid water turning into a gaseous water. First, before we actually go through and calculate anything, let's think about this. So our reaction that we have to go through and calculate is, delta G equals delta H. Oh my gosh, let's try that again. Delta G equals delta H minus T delta S. All right, so we are going to go through and we need to figure out what is delta H, what is delta S, so we can figure out any information going on with delta G. So if we have delta S, we're going to look at that first, right? So we can predict, is it going to be a positive or a negative number? Well, we're going from a liquid to a gas. So we're going from more order to more disorder. So we should see a positive change in your entropy value. So remember, delta S of your reaction equals the summation of delta S of your products minus the summation of your delta S of your reactants. You can find the numbers for liquid water to gas water in section 12 of your chemistry data booklet, but I'm just going to plug them in now. So you get positive 188.8 minus positive 70.0. This is going to give you a positive 118.8. Oh my gosh, horrible handwriting. Joules per Kelvin per mole. And remember, because all the value of delta H is in kilojoules, we're just going to go ahead and move this. So we get a positive 0.118 kilojoules per Kelvin per mole. So we have delta S. Yay, one of them. Now we need delta G. Delta H. So we're going to have delta H. And remember, delta H of reaction is the summation of delta H of your products minus the summation of delta H of your reactants. Again, the values can be found in section 12. So we have negative 242 minus a negative 286. That value is going to give us positive 44 kilojoules per mole. So we have found the two values, delta S and delta H. So what temperature is delta G going to be at equilibrium? All right, so we want delta G to equal 0. I do suggest, if you can, pause this video before I go through it and do the work yourself. If not, just follow me. So we already have our calculation up there, right? So we're going to have 0 equals positive 44 minus this unknown temperature times plus 0.1188, right? Do the math. So we get temperature equals 44 over 0.1188, and that's going to equal 370 Kelvin. Remember, we are working with the absolute temperature. What if they say, what is it in degrees Celsius, right? So you want to take a minus 273, and that value would give you it in degrees Celsius. So we know at 370 Kelvin, the reaction is at equilibrium. So anything above that temperature, spontaneous. Below that temperature, non-spontaneous. I would take a look at page 258 in your book, your chemistry book, and that's going to give you a table looking at how delta G is affected by delta H and delta S through different values. Calculating delta G values. All right, so the first one is delta G of a reaction from the delta G of formation. This can only occur when you have a reaction running at 298 Kelvin. So for us, we could never do delta G of formation. But guess what? Same calculation as before. You have delta G of your reaction equals the summation of delta G of your products minus the summation of your delta G of your reactants. We have not really changed anything here, so as long as you remember products minus reactants, you will find delta H, delta S, delta G if they're all standard. So there it is typed. Oops! Okay, so let's say we have a reaction, right? We have 2 aluminum plus iron 3 oxide makes 2 iron and aluminum oxide. Going again to section 12 of your chemistry data booklet, substitute those values in. So we have 2 aluminums, and just like any formation, a pure element does not have a value. Iron 3 oxide has a value of negative 742. Iron, no value. Aluminum oxide has a value of negative 1582. So go through and find the delta G of the reaction. So we're going to plug in. So delta G of your reaction equals negative 1582 minus negative 742. We get negative 840 kilojoules per mole. Because it is a negative sign, this is a spontaneous reaction. Remember, this calculation can only be done if it's saying it's coming from delta G of formation at 298 Kelvin. If it's not, we have to go this other route. So the other route is looking at delta G at varying temperatures. And this is where we come with the calculation of Gibbs free energy. So we already know the calculation for Gibbs free energy is delta G of your system equals delta H of your system minus the temperature times your delta S of your system, all measurable. So we're going to look at the decomposition of calcium carbonate. So calcium carbonate decomposes into calcium oxide and carbon dioxide. And we're going to look at it when this reaction runs at 500 Kelvin. So the first thing we need to figure out, and what we need to figure out we need, Well, to solve this, we need delta H and we need delta S, right? Okay, well, none of that's been given to us. Where can we find it? We can find it in section 12 of our data booklet, correct? So how do we go about and figure this out? Okay, so delta H, looking at section 12, this has negative 1207, this has negative 635, and negative 394. Okay, so going through and figuring this out, remember delta H you have your delta H of your reaction, so we have our summation, so negative 635 plus negative 394 minus a negative 1,207. We get a positive 178 kilojoules per mole. So you know already we're working with an endothermic reaction. So keep that in mind. All right. So then we need to figure out delta S. So delta S, as we know, is products minus reactants. Go to table 5 and you will table 12, and you will figure out the values. So we know calcium carbonate is 92.9. Calcium oxide is 39.7, and carbon dioxide is 214. Remember, all delta S values are positive because everything's above 0 Kelvin, but we're looking at what is the change. Are we going towards order or towards disorder? So products minus reactants. So we are going to take the summation of 39.7 plus 214 minus a positive 92.9. And we get a positive 160.8 joules per Kelvin per mole. This makes sense because look at the reaction. We go from one reactant to two products. We are making a gas, so we're increasing the moles of gas. So we are increasing entropy, therefore we should have a positive change. So you got the right number, or at least the right sign to the number. We want it in kilojoules, so positive 0.1608 kilojoules per Kelvin per mole. Now we have enough information to solve for delta G. All right, so delta G, we have our positive 178 minus, we're at 500 Kelvin, times positive 0.1608. And the value you get is positive 97.6 kilojoules per mole. So is this spontaneous or non-spontaneous? It's going to be non because it has a positive value. So we have done all these calculations before. We're just now doing essentially a bit larger picture and a summation of it all together. We've already done this with the first example, but we could figure out at what temperature is this reaction spontaneous then. So we know what to watch for. So we know that at equilibrium, delta G is going to be 0. So 0 equals delta H minus T delta S. So I'm going to rearrange this. T equals delta H over delta S. We already calculated those. Yes. So positive 178 over positive 0.1608. And we get 1106 Kelvin. Now that does not answer the question. That is at equilibrium. Let's answer the question. At spontaneous, at what temperature? So you'll have to say at any temperature at 11 or 1107 Kelvin and above is the correct answer. Again, you can put this into Celsius by taking minus 273 degrees Celsius. Real quickly, what does delta G look like at equilibrium? Well, we're going to deal with equilibrium in topic 7/17 in more detail, And this will make a lot more sense when we get there, but we can still look at what delta G is going to do. So equilibrium is the extent of the reaction. Does the reaction go all the way from reactants to products, or are you going to have no reaction, so no products, or are you going to have a mix of the two? And that's what an incomplete reaction looks like. All right, so when delta G is greater than positive 30 kilojoules per mole, and this is essentially, they've done thousands of different reactions, and this is the universal number they have found. Any reaction that has a positive delta G, or a delta G of positive 30 and above, no reaction takes place. So if you look over on your far right, this is an equilibrium setup. So the concentration of your products over the concentration of your reactants. When you have a double arrow, that means it's extreme. So if you have extreme value below 1, so 0.000000 value, so on and so forth, that means that this R has to be really high and the P is essentially non-existent to get such a low value. And so it tells you no measurable reaction has taken place. What about, so when the value of delta G is between 0 and positive 30, you're going to have an equilibrium reaction. So the concentration of products over reactants is just below the value of 1. So you're going to see a measurable mixture of the products and reactants. When delta G equals 0, it's at perfect equilibrium. So the amount of products equals the amount of the concentration of products equals the concentration of the reactants perfectly. When the value of delta G is less than 0, but greater than negative 30 kilojoules per mole, we're just flipping it. We're still at equilibrium, but now we have this value over here is greater than 1. So that means now products are holding a majority over reactants. And when delta G is less than negative 30 kilojoules per mole, we have a complete reaction. So all the measurable reactants have disappeared and we have an extremely large value over 1 and only products are measurable. And so we can relate that back to how spontaneous is that reaction, so on and so forth, and how many products do we expect in that.